Peter Atkins, The Laws of Thermodynamics, a very short introduction. Get ready to delve into the fascinating world of thermodynamics. In this summary of The Laws of Thermodynamics, a very short introduction by Peter Atkins, you will explore the fundamental concepts that govern our universe, from mechanical equilibrium to the idea of entropy. Understand the zeroth, first, second, and third laws of thermodynamics, and learn how they are applied in our daily lives, from steam engines to refrigerators. While these concepts may seem daunting at first, this summary will simplify and demystify them, giving you an accessible and engaging introduction to the world of thermodynamics.
Introduction to Thermodynamics. Thermodynamics is the study of systems and their surroundings. Different types of systems exist based on their boundaries: open, closed, and isolated. Mechanical equilibrium is the state where the pressure in different parts of a system is equal. It is crucial to thermodynamics. Thermodynamics attempts to understand how energy interacts with matter at the macro level. It is concerned with systems and their surroundings, which together form the universe. Different systems exist, depending on their boundaries, which could be open, closed, or isolated. In an open system, matter and energy can move in and out, while in a closed system, only energy can flow in and out, not matter. Isolated systems are not affected by their surroundings at all. An example of an isolated system is a vacuum flask. Mechanical equilibrium is the state where there's no net force acting on a system. It happens when the pressure in different parts of a system is equal. Two cylinders with a horizontal tube connecting them provide a visual illustration of mechanical equilibrium. If the pressure inside both cylinders is the same, the pistons connecting them will not move. If a third cylinder, C, is connected to A through a tube with movable pistons, but the pressure is equal, then there will be no tug-of-war between cylinders A and C. If we now detach C from A and connect it to B instead, C and B will be in mechanical equilibrium if the systems A and C and A and B are also in mechanical equilibrium. Understanding mechanical equilibrium is essential to thermodynamics because it provides a foundation for understanding how energy is transferred and work is done in thermodynamic systems. Once we understand how these systems work, we can use this knowledge to optimize performance, increase efficiency, and minimize waste. Unpacking the Zeroth Law. The Zeroth Law of Thermodynamics, also known as Law Zero, is the principle of thermal equilibrium between systems. Before discussing temperature or heat, this law must first be understood. By examining cylinders A, B, and C, we can determine if they are in thermal equilibrium. The Zeroth Law infers a similar property to mechanical equilibrium, which is temperature. If two systems have the same temperature as a third system, then those two systems also have the same temperature. Exploring the atomic world. This summary delves into the world of atoms and statistical thermodynamics, beyond the classical thermodynamics of the 19th century. The Boltzmann distribution is used to understand how groups of atoms behave when distributed across energy states and how this relates to temperature. Atoms have defined energy states, and the largest group is always in the lowest energy state or the ground state. As temperature increases, more groups of atoms migrate to higher energy states, and there are fewer groups in lower energy states. The Boltzmann distribution provides a molecular definition of temperature, crucial for explaining various phenomena. Understanding the first law of thermodynamics. The first law of thermodynamics states that the internal energy of an isolated system is constant unless work is being done on the system. To comprehend this law, we must first understand the concept of work as a mechanical force. Work is the motion against an opposing force, such as a pulley lifting a heavy object or a person struggling to remain upright in the wind. All systems have energy, but different systems have different amounts of energy and, therefore, varying capacities for work. When work is being done, the system's internal energy changes, much like climbing a mountain. However, regardless of the path taken to reach the top, the altitude remains the same. Heat transfer is the process by which energy is transferred from a system to its surroundings, which occurs unless the system is fully isolated. An isolated system that does no work maintains its constant internal energy, constituting the first law of thermodynamics. The second law of thermodynamics in everyday life. Steam engines and everyday occurrences provide insights into the second law of thermodynamics, which states that heat cannot be transferred from high-temperature systems to low-temperature systems without work being done elsewhere. The second law of thermodynamics can be challenging to understand, but by examining concrete examples such as steam engines and everyday occurrences, we can grasp its principles better. Steam engines are complex engineering machines that consist of hot energy sources, devices that transform heat into work, and cold sinks that extract unused energy. The cold sink is a crucial part of every steam engine and helps us explain the second law of thermodynamics. It states that when heat is converted into work, some heat is transferred to a system's surroundings. In everyday life, we can observe spontaneous heat transfer such as when a mug of boiling water makes the mug itself hotter. No pistons or electricity are required for this spontaneous process. However, when you forget your mug of tea and decide to make an iced tea popsicle, you put it in a freezer, and it gradually gets colder as the freezer works to transfer heat from the tea to the surroundings. This process is not spontaneous, and it requires work, such as fuel being combusted to generate electricity to keep the freezer running. From these examples, we can conclude that heat cannot transfer from high-temperature systems to low-temperature systems without work being done elsewhere. This is a valuable insight into the second law of thermodynamics that helps us understand the transfer of heat in everyday occurrences. Understanding entropy in thermodynamics. Heat transfer without work leads to entropy increase in a system and its surroundings. This concept can be better explained using the example of a sneeze. When we transfer heat to a system, the entropy level changes depending on the initial entropy of the system and the size of the heat transfer. The second law of thermodynamics states that the entropy of the universe increases during spontaneous changes. Hence, heat being transferred without work leads to an increase in the entropy of a system and its surroundings. Thermodynamics Unveiled. The second law of thermodynamics and entropy. Have you ever wondered whether it's possible to have a heat engine without a cold sink? The answer is no. In this segment of the book, we explore the second law of thermodynamics and its impact on spontaneous changes. We also take a closer look at entropy and its significance in this context. The second law of thermodynamics states that the entropy of the universe must always increase during spontaneous changes. This means that a heat engine without a cold sink is impossible. Without a cold sink, the entropy won't change, as entropy only changes when heat is transferred and not when work is done. Therefore, it's vital to have a cold sink for entropy to increase within the universe. Our second statement regarding spontaneous heat transfers from hot to cold objects explains entropy. When energy leaves a cold object in the form of heat, its entropy decreases. On the other hand, when heat enters a hot object, its entropy increases, but only by a smaller amount. This results in an overall decrease in entropy, which according to the second law, cannot be spontaneous without any work. In conclusion, we verified the second law of thermodynamics and how entropy affects spontaneous changes. Although we've discussed that entropy concerns disorder, its full significance is yet to be explored, which we'll cover in the next part. Understanding entropy and disorder. Entropy, in thermodynamics, is a measure of disorder. At a molecular level, when the temperature of a group of atoms increases, atoms migrate to higher energy states, resulting in a wider range of occupied energy levels. Predicting the energy level of a single molecule becomes more uncertain with increased disorder. At absolute zero, only the lowest energy state is occupied by molecules, resulting in zero uncertainty, zero disorder, and zero entropy. Understanding thermodynamic taxation. When a system produces heat, it pays a heat tax, and when it produces work, it pays a work tax. This is because of the second law of thermodynamics, which states that any spontaneous change is accompanied by an increase in entropy, which we'll call an entropy tax. The enthalpy of a system helps physicists work out how much heat a system is capable of generating, while Helmholtz and Gibbs energy help them keep track of changes. The final law of thermodynamics. The third law of thermodynamics ties together the concepts of the previous laws and states that the entropy of all perfectly crystalline substances at absolute zero temperature is zero. This law only applies to perfectly crystalline substances, as they have zero entropy at absolute zero temperature. Trying to cool an object to absolute zero through cyclic processes is impossible, and this is due to the cyclical processes never being able to bring an object to absolute 0 Kelvin. Understanding the third law can help in comprehending the behavior of degenerate substances and the importance of cyclical processes in thermodynamics.
In conclusion, The Laws of Thermodynamics, a very short introduction, by Peter Atkins provides a thorough and engaging exploration of the fundamental concepts of thermodynamics. From understanding the importance of mechanical and thermal equilibrium to unraveling the mysteries of entropy, this book's summary gives readers key insights into the laws that govern our universe. Through the examination of the zeroth, first, second, and third laws of thermodynamics, the book demonstrates how these concepts govern everything from the workings of steam engines to the cooling processes of refrigerators. Overall, this summary offers a comprehensive, easy-to-understand guide to the fascinating world of thermodynamics.